In this video, we're going to do some practice problems with torque. And torque being the rotational version of force, it has a few different definitions, just like force did. The first one is going to be our conversion from force to torque. And this is going to be the lever arm definition. The lever arm definition is useful because it helps us break up these forces when they are coming in at angles, which happens frequently enough. It is going to allow us to focus only on the part of the force that's actually perpendicular to the rotating object. And then we have this second definition. This is a torque equals a moment of inertia times alpha, which is our angular acceleration. This is Newton's second law in the context of torque. So remember, Newton's second law was F net equals ma. This is really the same thing. Our rotational inertia is just our rotational version of mass. That's I. And then our angular acceleration, that's just our angular version of our regular acceleration. And then F net becomes torque net. And then, of course, with that same idea, if we have multiple torques on an object, then they're going to be summed together to create a net torque. So this is our net torque definition. And torque we always represent with the Greek letter tau, which is like a T, except instead of being a T, it has a squiggly tau. That's how I always draw it. So let's start with this idea. Let's use this problem right here. I've got an angle of 40 degrees. I've got a force of, let's just say, 30 newtons being applied at a distance of, let's say, 2 meters. What is the net torque produced on this body right here? Well, that would be simple enough to figure out. I'm going to have a torque that's going to be equal to, what do I have in this case? Well, I've got a force, I've got an angle, and I've got a lever. So I've got Fr sine theta. So that's the definition I'm going to be using here. And so my force would be 30. My r, my radius, would be 2. And that would be the sine of 40 degrees. So I should be able to punch that into a calculator and get a net torque. And when I put all of that in, I get a torque, a net torque of 38.6 Newton meters. Now, let's give this object some mass, and let's figure out its angular acceleration. Let's give it a mass of, let's just say 3 kilograms. And then it's got that distance of 2 meters. Let's say that's the overall distance of the object. Now I can apply my definitions for my moment of inertia. Now generally the moment of inertia will be given. You won't have to figure it out. You won't have to refer back to those equations that often. But in this case I didn't already have it figured out. So the moment of inertia of a rod spinning around one end is going to be 1/3 ml squared. And so this is going to be 1/3 times our 3 kilograms, that's convenient, times our L squared, which is 2 squared. And so 3 cancels out 3, and we get 2 squared, we get 4. Our moment of inertia for this rod is 4. So I want to know, what is my angular acceleration? That's going to be found by taking my torque, my net torque, equals my I alpha. And so that's going to be 38.6 equals 4 alpha. Divide both sides by 4. And I get an angular acceleration of 9.65 radians per second squared. Okay, so that was straightforward enough. We're going to need to be able to apply this kind of problem. We're going to need to be able to do this kind of problem where we're given a force, we're given an angle, we're given a lever arm, and we need to figure out what is the torque acting on this object. Or maybe we're given the torque and we need to figure out the force that was acting on it. Regardless, either way we should be able to work with that equation. We should also be able to work with this definition. We should be able to, given 2 of these variables, solve for a third one. And then we should also be able to work with multiple forces. So that's this problem that I have right here. So let's give each of these forces a definition. Let's apply some kind of angle to each of those thetas. All right, now we've got definitions for our forces, our angles, and our radiuses. So let's apply all of these together to figure out my net torque, because each of these is going to have its own individual torque. My net torque is going to be equal to the torque at 1 plus the torque at 2 plus the torque at 3. Well, since torque at 1, let's just call this would be F1. This would be torque would be equal to F1 times R1 times the sine of theta 1. I can replace each of these variables with that same definition. And so my net torque will actually be the sum of each of those products. So ultimately, this becomes my definition for my net torque, is each of these equations being substituted in for their subsequent torque. Each of these forces will apply a torque to this rod, and then all together they'll have some kind of net torque. So let's go ahead and punch our numbers in here and create an actual equation. Now with all of my numbers in there, I can go ahead and calculate for my net torque. Now if I just punch all of those numbers in as is, I get 65.5 Newton meters. But that's not right, is it? We're missing something. And that's going to be because according to our definitions, we need a positive and negative. So which way is going to be positive or negative? Is it going to be up or is it going to be down? Well, that's a really good question, because if I kept applying these forces, if I applied these same forces while moving, eventually my rod would be turned around and suddenly my F1 would be on bottom, pushing up, while my F2 and 3 were on top, pushing down. If I just try to apply a straight up is positive and down is negative methodology, then everything's going to flip by the time I get to the other side. That also doesn't help me if I'm perpendicular, if I'm straight up and down. And so we need a definition of positive and negative that fits in line with rotation. And that is going to be clockwise and counterclockwise. And so this is going to be counterclockwise, and that's going to be our positive direction. Whereas our clockwise direction is going to be our negative. So in this case, now we need to identify all of the forces that are counterclockwise. Well, F2 and F3, those are both, F2 and F3 are both counterclockwise, so those are both positive. And then our F1 is going clockwise, so that's going to be negative. So this should be negative 15 times 3 times sine of 30. So let's punch that into our calculators and get our proper values. Now, with those positives and negatives in the right spots, I get 20.5 Newton meters for my net torque.